April 7th, 1989, 11:03 a.m., Norwegian Sea, 180 kilometers southwest of Bear Island. The fire alarm pierced through Compartment 7 at 335 meters depth. Within seconds, temperature sensors registered readings climbing past operational limits, first 400 degrees C, then 600 degrees C, accelerating toward conditions no submarine designer had anticipated. A short circuit had ignited hydraulic fluid near the turbine systems. The watertight doors sealed automatically, as designed, but the flames found pathways through cable penetrations in the bulkheads, spreading forward through the titanium-hulled vessel that had once set depth records. 11 minutes after the alarm sounded, K-278 Komsomolets broke the surface of the 2 degrees Celsius water. Captain First Rank Evgeny Vanin's distress call went out at 11:16. The crew expected rescue within the hour. 5 hours later, the submarine would sink to 1,180 meters, taking with it 2 nuclear-armed torpedoes, a pressurized water reactor, and questions that would echo for decades. In the shipyards of Severodvinsk during the early 1980s, engineers from the Rubin Design Bureau assembled what would become the Soviet Navy's most ambitious underwater prototype. The Project 685 submarine, designated K-278 and later named Komsomolets, represented a fundamental departure from conventional submarine construction. Where other vessels use steel hulls welded in traditional dry docks, this boat required specialized facilities flooded with argon gas. Workers in breathing apparatus resembling spacesuits welded titanium alloy 48T, a material as strong as steel but 45% lighter. The process demanded precision. Any contamination from oxygen during welding would compromise the hull's integrity. The titanium inner hull spanned 117 meters and would displace 8,000 tons when submerged. This construction enabled K-278 to withstand water pressure of 1,500 pounds per square inch, approximately double what American Los Angeles-class submarines could endure. The design goal was explicit: create a platform capable of operating at depths where NATO's Mark 48 torpedoes, limited to 800-meter pursuit depth, could not follow. On August 4, 1984, K-278 descended to 1,020 meters in the Norwegian Sea, establishing a military submarine depth record that would outlive the Soviet Union itself. The submarine's single OK-650B3 pressurized water reactor generated 190 megawatts, driving a single propeller to 30 knots, respectable by Western standards but typical for Soviet designs that prioritized maneuverability and depth over acoustic stealth. 6 533mm torpedo tubes occupied the bow. Among the standard 22 torpedoes, K-278 carried specialized Shkval supercavitating rockets capable of underwater speeds approaching 200 knots. These weapons employed a rocket motor and created a gas bubble around themselves, allowing them to travel through water with minimal resistance, technology that remained classified for years after the submarine's loss. Advanced automation reduced the crew requirement to 57 personnel, later increased to 64, 30 officers, 22 warrant officers, and 12 petty officers and seamen. This lean manning reflected Soviet confidence in automated systems, but also created a vulnerability. Where American nuclear submarines of comparable size operated with crews exceeding 120, providing redundancy during casualties, K-278's systems left little margin for major emergencies. The submarine's most distinctive safety feature, an escape capsule mounted in the sail, could theoretically save the crew from underwater disasters. This spherical pod, accessed from the second and third compartments through a protected safety zone, would prove tragically inadequate when needed most. After years of testing, K-278 Komsomolets transitioned from experimental prototype to operational warship in 1988. Captain First Rank Yuri Zelensky, who had commanded the boat during its record dive, received commendation. In October 1988, the submarine earned an unusual honor, an actual name. Most Soviet submarines were known only by their hull numbers and NATO reporting names. Komsomolets, meaning member of the Communist Youth League, signified the Navy's pride in this technological achievement. The submarine deployed on its third operational patrol on February 28, 1989, departing Zapadnaya Litsa Naval Base, under a new commander, Captain First Rank Evgeny Vanin. His crew lacked the extensive deep-diving experience of the original team that had pushed K-278 to its record depths. The fire that would doom K-278 Komsomolets began with a cascade of failures that investigations would later trace to a design vulnerability. At 11:03 on April 7th, while the submarine operated at 335 meters depth, an electrical short-circuit occurred in Compartment 7, the aftmost section housing steering gear and machinery systems. The malfunction ignited hydraulic fluid near a turbine assembly. Within seconds, temperatures began climbing beyond operational parameters. The crew reacted according to procedure. Watertight doors between compartments sealed immediately. Damage control teams donned breathing apparatus and began fire suppression efforts. But the fire in Compartment 7 was fed by a design flaw that no training exercise had anticipated. High-pressure airlines, carrying 8,000 pounds per square inch, ran through the compartment to supply the emergency ballast blow system. When Captain Vanin ordered the submarine to surface, a section of this piping, weakened by the intense heat, ruptured. What happened next transformed a manageable fire into a catastrophe. The ruptured airline injected massive volumes of compressed air directly into the flames, turning Compartment 7 into what one naval analyst would later describe as a blast furnace. Temperatures reached 1,000 degrees, hot enough to compromise titanium structural elements. The pressurized air fanned the fire through cable penetrations in the bulkheads, spreading smoke and heat forward, even through sealed watertight doors. Electrical systems began failing throughout the submarine. The reactor scrammed automatically at 11:09, cutting off propulsion. Control of the vessel became increasingly tenuous as cables burned through and monitoring systems went dark. Without power to the hydraulic systems, the submarine could not maintain its trim or depth without emergency measures. At 11:13, with temperatures in Compartment 7 approaching 2,000 degrees, the emergency ballast blow finally forced K-278 to the surface. The submarine broke through at 11:14, 11 minutes after the fire began. Captain Vanin immediately transmitted a distress call. His position, approximately 180 kilometers southwest of Bear Island, in international waters where the Norwegian Sea met the Barents Sea. Water temperature registered 2 degrees. Wind conditions were deteriorating. The nearest Soviet naval facilities lay several hundred kilometers to the southeast. On the surface, K-278's situation remained critical. The fire continued to burn, now fed by the very system designed to save the submarine. Compressed air leaks throughout the aft section sustained the flames even as damage control parties tried to contain them. Smoke filled multiple compartments. The breathing system, compromised by the heat, began failing. Crew members working in the aft sections collapsed from smoke inhalation. At approximately 11:45, Captain Vanin ordered the crew to abandon ship to the open deck. 69 men had been aboard when the patrol began. Most now assembled topside, awaiting rescue while the submarine burned beneath them. Soviet naval doctrine presumed that rescue forces could reach a surfaced submarine within 1 to 2 hours in these waters. Captain Vanin radioed updated position reports and maintained communication with Northern Fleet headquarters. The crew waited in their survival suits as the submarine settled lower in the water, the fire consuming internal structures and flooding gradually pulling the bow down. The first aircraft arrived overhead at approximately 12:30, 90 minutes after K-278 surfaced. The planes dropped inflatable rafts into the rough seas, but wind conditions scattered them beyond the crew's reach. The men watched as orange rafts drifted past in the building swells. Water temperature remained at 2 degrees, cold enough to induce hypothermia in 15 to 20 minutes for anyone immersed without adequate protection. The crew stayed aboard K-278 as long as structurally possible, huddling on the casing as the submarine settled deeper. By 15:09, more than 4 hours after surfacing, K-278's bow had dipped sharply. Flooding through the damaged forward sections accelerated. Captain Vanin and his senior officers assessed their situation. The submarine would sink within minutes, rescue vessels had not arrived, and the crew faced imminent exposure to Arctic waters. The decision was made. At 15:08, most of the crew entered the water. Some men inflated personal flotation devices. Others formed groups attempting to conserve body heat. The water's temperature began its work immediately. Even through survival suits, the cold penetrated. Extremities went numb first. Shivering started within minutes. Cognitive function began degrading after 10 minutes of immersion. The men could see aircraft overhead, but no surface vessels. At 15:15, 7 minutes after the crew abandoned ship, K-278 Komsomolets sank. The submarine's bow tilted sharply downward, and the vessel slipped beneath the surface, leaving behind swirling water and debris. Captain Vanine and 4 other men remained aboard, having stayed to ensure the crew evacuated. As the submarine went down, these 5 men entered the escape capsule in the sail and activated the ejection system. The spherical escape pod separated from the sinking submarine and began its ascent. But the system had never been tested under actual emergency conditions. The capsule broached the surface, partially flooded and filled with toxic gases from the fire below. The hatch mechanism jammed. Of the 5 men sealed inside, only one, a young warrant officer, managed to escape through a damaged port before the capsule took on more water and sank. Captain Evgeny Vanine was among those trapped inside as the escape pod descended back to the seafloor with the wreck. The civilian floating fish factory Alexei Klobistov arrived at 16:36, 81 minutes after K-278 sank, more than 5 hours after the submarine first surfaced. The rescue ship pulled 25 survivors and 5 bodies from the water. Many men had already died from hypothermia. Others were in late-stage hypothermia, their core temperatures dangerously low. 3 more would die aboard the rescue vessel despite warming efforts. The final casualty count stood at 42 dead from a crew of 69. Only 4 men had died from the fire itself. The remaining 38 perished in the water or in the failed escape capsule, deaths that could have been prevented with faster rescue response. Within hours of the sinking, the Northern Fleet initiated salvage planning. The immediate concerns were practical and political. K-278 carried 2 torpedoes armed with nuclear warheads, each containing plutonium. The submarine's OK-650B3 reactor held uranium fuel that would remain radioactive for decades. All of this now rested at a depth of 1,180 meters, more than a mile down, in one of Europe's richest fishing grounds. Norway, whose exclusive economic zone lay nearby, immediately demanded information about radiation risks. Soviet officials provided initial assessments. At that depth, they argued, any radiation leakage would be minimal and quickly diluted. The titanium hull and reactor vessel would resist corrosion for centuries. The nuclear warhead casings were designed to withstand deep ocean pressure. Senior naval officers stated publicly that K-278 posed no significant environmental threat. These assurances did little to calm Norwegian concerns. The area where K-278 sank supported fishing operations worth billions of dollars annually. Even minor radioactive contamination could devastate the industry. In June 1989, 2 months after the sinking, the oceanographic research vessel Academic Mstislav Keldysh deployed deep-sea submersibles to locate the wreck. The manned submersibles found K-278 resting upright on the seabed at 1,680 meters. External examination revealed the extent of fire damage: scorched metal around the sail, deformation in the aft sections, and visible cracks along portions of the hull. The escape capsule lay nearby, partially buried in sediment. Video footage transmitted from the submersibles showed twisted metal and debris scattered around the primary wreckage. The submarine's structure appeared largely intact, though the intense heat from the fire had clearly compromised some sections. Soviet and later Russian expeditions returned periodically. In August 1991, as the Soviet Union entered its final months, investigators used submersibles to examine the interior of K-278's bow section. They discovered evidence of an explosion in the forward torpedo compartment. Whether this occurred during the fire or during the sinking remained unclear. The explosion had created a massive breach in the bow, a structural failure that eliminated any possibility of raising the submarine intact. A 1992 expedition conducted extensive sampling of water, sediment, and marine organisms around the wreck site. Norwegian scientists participated in this survey, taking their own samples for independent analysis. Initial results showed no detectable radiation above background levels in the water column more than 50 meters from the wreck. Sediment samples from the immediate vicinity showed slight elevation, but nothing approaching dangerous levels. Marine life samples revealed no bioaccumulation of radioactive isotopes. Then, in 1993, a joint Russian, Norwegian, Dutch-American expedition detected cesium-137 in water samples taken near K-278's reactor compartment. The readings were not high, several orders of magnitude below levels considered dangerous to human health, but they confirmed that radioactive material was escaping from the wreck. A ventilation pipe leading from the reactor compartment was identified as the primary leakage point. The discovery of active radiation leakage transformed K-278 from a tragic loss into an ongoing environmental concern. Cesium-137, a fission product with a half-life of 30 years, indicated that nuclear fuel inside the reactor was slowly breaking down and that its containment had been compromised. The amounts detected remained small, but the implications were significant. If the reactor's structural integrity was degrading, leakage rates could increase over time. A 1994 expedition focused on sealing the identified leakage points. Russian submersibles descended to the wreck, carrying specialized equipment and sealant materials. Working at 1,680 meters depth, operators attempted to plug the ventilation pipe and other potential breach points. The work proceeded slowly. The intense water pressure, near zero visibility, and corroded condition of the hull surfaces made operations difficult. Several holes in the submarine's outer hull were successfully sealed with caps and quick-hardening epoxy compounds. Russian officials announced that the most significant leakage pathways had been closed. Monitoring continued. Norwegian authorities, whose waters and fisheries were potentially at risk, insisted on annual surveys. Each summer, Norwegian research vessels would transit to the K-278 site and collect water and sediment samples. These samples were analyzed for cesium-137, strontium-90, and other radioactive isotopes. Through the late 1990s, readings remained relatively stable. The sealed leakage points appeared to be holding. Cesium-137 levels in the water column remained detectable only in samples taken within a few meters of the wreck itself. In 1997, the Norwegian Defence Research Establishment published a comprehensive study on K-278's long-term environmental impact. Using corrosion models and structural analysis, researchers concluded that neither the submarine hull nor the reactor vessel will be destroyed by corrosion for at least 1,000 years. The titanium hull, despite the fire damage, would resist seawater corrosion far longer than steel. The reactor vessel itself, constructed from thick steel alloys and located in the submarine's interior, was even more resistant. The report projected that significant structural failure, the kind that might release large quantities of radioactive material, would not occur during the period when the nuclear fuel remained most dangerous. This reassuring assessment came with caveats. The study noted that the 1993 sealing operations had not been fully effective. Some leakage pathways remained open. The report also emphasized that monitoring must continue indefinitely. While catastrophic release scenarios were unlikely, gradual leakage would persist. Marine organisms in the immediate vicinity of the wreck showed slightly elevated cesium-137 levels, not dangerous to humans who might consume these fish, but indicative of ongoing bioaccumulation in the local food chain. The technical question of raising K-278 was periodically debated. Some argued that removing the submarine would eliminate the environmental risk entirely, but engineering analyses consistently reached the same conclusion. The wreck was too deep, too damaged, and too contaminated with radioactive material to salvage safely. The cost was estimated at over $1 billion, an impossible sum for Russia's struggling post-Soviet economy. More critically, attempting to lift the wreck risked breaking apart the hull and releasing radioactive material directly into the water column at shallower depths, where it would more readily enter the food chain. In 2007, Russian researchers conducted what would be their last major expedition to K-278 for more than a decade. Using remotely operated vehicles, they performed detailed video surveys of the wreck's condition 18 years after the sinking. The footage revealed ongoing deterioration. New cracks had appeared in the outer hull. Some sections showed significant corrosion, particularly around welded seams where dissimilar metals met. The reactor compartment's ventilation system, the primary known leakage point, showed visible damage from both the original fire and subsequent corrosion. Water samples collected during this expedition confirmed that leakage continued. Cesium-137 readings near the ventilation pipe ranged from 10 to 100 becquerels per litre, well above the 0.001 BQL typical for the Norwegian Sea, but far below levels considered immediately dangerous. The pattern suggested intermittent release. Samples taken at different times showed varying contamination levels, possibly related to underwater currents, changing pressure differentials within the wreck. Norwegian authorities maintained their monitoring program throughout the 2000s and 2010s, but technological limitations constrained the data. Research vessels could lower sampling equipment to the wreck site, but precise positioning was difficult. Without visual confirmation, scientists could not be certain exactly where samples were being collected relative to known leakage points. Sediment cores from the seabed showed cesium-137 distributed in a pattern consistent with slow leakage over many years, but the resolution was insufficient to determine if leakage rates were increasing. The breakthrough came in 2019, when Norwegian researchers deployed a sophisticated remotely operated vehicle, the Airgear 6000, capable of both precise navigation and real-time video at extreme depths. For the first time since 2007, scientists could observe K-278 while simultaneously collecting samples from specific locations. The expedition launched in early July, 30 years after the sinking. The ROV located K-278 on its first dive. Video transmitted to the surface showed a haunting scene. The submarine's scorched hull rested upright on the sediment, its sail rising from the debris field, twisted metal and equipment scattered around the wreckage. The titanium hull, despite 3 decades on the seafloor, retained its basic shape, but the fire damage was evident. Sections of the outer hull had collapsed inward. The escape capsule lay partially buried nearby, a reminder of the tragedy that had unfolded above. The Aegir 6000 maneuvered close to the ventilation pipe, identified in previous expeditions as a leakage source. The ROV's cameras captured something unexpected, a visible plume or cloud emanating from the pipe opening. Whether this was radioactive cesium mixing with seawater, sediment disturbed by the ROV's thrusters, or some other phenomenon was unclear. The ROV extended its sampling arm and collected water directly from the plume. Laboratory analysis of that sample revealed cesium-137 concentrations of 800 becquerels per litre, 800,000 times higher than normal Norwegian sea levels. Other samples from the same pipe showed varying concentrations, one at 100 BQL, 2 at 30 BQL, and one showing no elevation above background. The pattern confirmed intermittent release, likely driven by internal pressure changes within the deteriorating reactor compartment. The 2019 findings generated immediate media attention. Headlines emphasized the 800,000-fold increase, a dramatic figure that seemed to herald environmental catastrophe. But Norwegian scientists carefully contextualized the data. Expedition leader Hilde Elise Heldal of the Institute of Marine Research explained that the highest readings came from inside a ventilation pipe, essentially sampling directly from the source of the leak. Samples collected even a few meters away from the pipe showed no detectable elevation above background levels. The rapid dilution resulted from basic physics. At 1,680 meters depth, ocean currents dispersed the leaked cesium quickly. The massive volume of water in the Norwegian and Barents Seas provided enormous dilution capacity. Even if all the cesium-137 in K-278's reactor were released simultaneously, a worst-case scenario far beyond the observed gradual leakage, models predicted the impact on regional fish populations would remain below detection thresholds. For context, Heldal noted that Norwegian food safety regulations after the 1986 Chernobyl accident had set cesium limits at 600 becquerels per kilogram for food products. The 800 BQL reading from K-278, while dramatically higher than background, remained below this standard established for human consumption. Marine organisms living near the wreck would accumulate some cesium, but fish caught in commercial fishing areas, typically dozens of kilometers from the wreck site, showed no measurable contamination attributable to K-278. The Norwegian Radiation and Nuclear Safety Authority emphasized that monitoring would continue. Justin Gwynn, A researcher with the authority pointed out that the Aegir 6000 expedition represented the most detailed examination of K-278 to date. The ROV had collected biological samples directly from the wreck, organisms growing on the submarine's hull that would show maximum bioaccumulation. These specimens were being analysed to determine long-term ecological impacts. Russian officials provided limited public response to the 2019 findings. The submarine fell under Russian jurisdiction as a military wreck in international waters. Russia had conducted its own monitoring through 2007, but had not participated in recent Norwegian expeditions. In private communications, Russian scientists reportedly told Norwegian counterparts that the findings aligned with their own historical measurements and expectations for the wreck's condition. The practical question remained: what, if anything, should be done about K-278? The options were limited. Raising the submarine was still technically infeasible and prohibitively expensive. Attempting salvage would likely cause more environmental harm than leaving the wreck in place, as breaking apart the hull during lifting would release radioactive material at shallower depths. Additional sealing operations faced similar challenges. Working at 1,080 meters depth, with severely corroded and fire-damaged surfaces, offered little promise of success. The consensus among Norwegian and international experts was that continued monitoring represented the most prudent approach. K-278 would remain on the seafloor, gradually leaking small amounts of cesium-137 that the ocean would dilute to insignificance. The titanium hull would eventually fail completely, probably centuries from now. By that time, the radioactive isotopes would have decayed to less dangerous levels. The site would remain marked on Norwegian charts, and fishing vessels would avoid the immediate area as a precaution. The investigation into K-278's loss had begun immediately after the sinking, but conclusive findings proved elusive. A state commission examined the accident, interviewing survivors and reviewing design documentation. Their initial conclusion focused on numerous technical imperfections in the submarine's design, a verdict that essentially blamed the engineers at Rubin Design Bureau. The Bureau vigorously disputed this finding. Dmitry Romanov, deputy designer on the Project 685, later wrote a detailed defense arguing that the fire resulted from operational factors, not design flaws. An independent commission, convened separately, reached different conclusions. Their investigation identified specific vulnerabilities. The routing of high-pressure airlines through Compartment 7 created a catastrophic failure point. When fire weakened these lines and they ruptured, the released compressed air at 8,000 psi turned a containable fire into an inferno. The compressed air fed the flames, spread smoke and toxic gases through cable penetrations, and made traditional fire suppression impossible. The crew's training and experience also drew scrutiny. K-278's original crew, led by Captain Yuri Zelensky during the record-breaking depth tests, had extensive experience with the submarine's unique systems. Captain Evgeny Vanin's crew, assigned for the 1989 patrol, had less time with the boat. Some investigators suggested that a more experienced crew might have contained the fire more effectively. Others countered that no amount of training could overcome the fundamental design vulnerability of routing pressurized airlines through a machinery space prone to electrical fires. The escape capsule's failure became particularly controversial. Designed specifically to save the crew during underwater emergencies, the system had never been tested under actual disaster conditions. When activated during K-278's sinking, the capsule ejected successfully but surfaced partially flooded and filled with toxic gases. The hatch mechanism jammed. Of 5 men inside, only 1 survived. The investigation revealed that the capsule's ventilation system drew air from inside the submarine, meaning it was contaminated with smoke and toxic combustion products before ejection. This design oversight transformed a supposed safety feature into a death trap. The formal investigation concluded in 1998, 9 years after the accident, without assigning individual responsibility. The findings documented multiple contributing factors: design vulnerabilities, equipment failures, crew training deficiencies, and inadequate rescue response. But no single person or organization was held accountable. The accident report emphasized that K-278 was a prototype, testing new technologies under operational conditions. Some level of risk was inherent in such vessels. For the families of the 42 dead, this conclusion offered little comfort. In 1993, Vice Admiral Chernoff, retired, who had commanded the submarine group that included K-278, founded the Komsomolets Nuclear Submarine Memorial Society. The charity initially focused on supporting widows and orphans of Komsomolets' crew. Its mandate soon expanded to assist families of all Soviet and Russian submariners lost at sea, a group numbering over 500 from Cold War accidents alone. The immediate aftermath of K-278's loss had exposed systemic problems in Soviet submarine operations. The slow rescue response, over 5 hours between surfacing and the arrival of the first rescue ship, was inexcusable given the proximity to northern fleet bases. Aircraft had arrived quickly and dropped rafts, but these proved inadequate in rough seas. No helicopter-capable rescue vessels had been positioned to respond rapidly to submarine emergencies in these waters. Soviet naval doctrine had emphasized offensive capability while accepting higher accident rates than Western navies tolerated. Throughout the Cold War, Soviet submarines suffered catastrophic losses at a rate several times higher than American boats. Poor radiation shielding, weak safety culture, and willingness to operate experimental systems in frontline service all contributed. K-278 fit this pattern, a prototype with known vulnerabilities deployed on operational patrol with a partially trained crew and inadequate emergency support. The loss also highlighted automation's limitations. K-278's reduced crew size, achieved through advanced automated systems, looked impressive on paper. But during the fire, when systems failed cascadingly, the small crew was overwhelmed. They could not simultaneously fight the fire, maintain control of the submarine, and prepare for evacuation. American submarines carried larger crews specifically to maintain capability during battle damage or casualties. The K-278 experience validated this conservative approach. International implications extended beyond Soviet naval operations. K-278 carried nuclear weapons in international waters and sank in fishing grounds shared by multiple nations. The accident demonstrated that nuclear submarines pose transnational environmental risks. While this was theoretically understood, K-278 made it concrete. A single submarine accident could contaminate waters belonging to no single nation, creating monitoring and cleanup obligations that would span decades. Norway's response set precedents. Norwegian authorities insisted on independent monitoring and refused to simply accept Soviet assurances about radiation safety. The annual expeditions to K-278's wreck site, maintained for 30 years, represented a model for international oversight of nuclear accidents in shared waters. This monitoring relationship survived the Soviet Union's collapse and continued through multiple changes in Russian government. The April 7th anniversary became a day of remembrance in the Russian Navy. Each year, ceremonies honored not only Komsomolets' crew, but all submariners lost at sea. The date took on particular significance as other submarine disasters followed: Kursk in 2000, K-159 in 2003, and others. The commemorations emphasized sacrifice and duty while typically avoiding detailed discussion of the accident's causes, a tendency that some critics argued prevented meaningful reforms in submarine safety culture. For naval architects and submarine designers, K-278 provided hard lessons. Titanium hulls enabled greater depths, but introduced fabrication challenges. Automated systems reduced manning, but eliminated redundancy. Escape capsules required rigorous testing under actual emergency conditions. High-pressure air systems needed better protection from fire. Each lesson was written in the lives of 42 men who died in Arctic waters that April morning. 3 decades after K-278's sinking, the wreck remained a unique environmental case study. Unlike many nuclear submarines lost during the Cold War, K-278 received sustained long-term scientific monitoring. This created an unusually complete data set on how nuclear submarines deteriorate in deep ocean environments and what environmental impacts result. The data showed that worst-case scenarios had not materialized. Cesium-137 was leaking from the reactor, but ocean dilution reduced concentrations rapidly. Fish caught in commercial fishing areas showed no elevated radiation levels attributable to K-278. Sediment contamination remained localized within a few hundred meters of the wreck. Marine organisms living directly on the submarine's hull accumulated measurable cesium, but these organisms were not part of commercial fisheries. Yet the leak continued. The 2019 expedition's 800 BQL reading indicated that 30 years of seawater exposure had not sealed the reactor compartment through natural corrosion products. The ventilation pipe leaked intermittently, sometimes producing samples with high contamination, sometimes showing normal background levels. This pattern suggested that internal water circulation within the wreck varied with external currents and pressure changes. Modelling studies examined long-term projections. The cesium-137 in K-278's reactor would decay with a half-life of 30 years. By 2049, 60 years after the sinking, half of the original cesium would have transmuted to non-radioactive barium-137. By 2109, only 1/4 would remain. Eventually, radioactive decay would reduce the material to negligible levels, even if all of it leaked out. But K-278 contained other radioactive isotopes with different half-lives. Strontium-90, another fission product, had a similar half-life to cesium-137. Plutonium-239, present in the nuclear warheads carried by the torpedoes, had a half-life of 24,000 years. The torpedoes' plutonium cores were encased in multiple protective layers, and monitoring had detected no plutonium leakage. But if the warhead casings eventually failed, possibly centuries from now, plutonium could enter the marine environment. The Norwegian Institute of Marine Research developed protocols for continued monitoring. Annual or biennial expeditions would collect water and sediment samples. Biological sampling would track any changes in marine organism contamination levels. Advanced ROV systems would document the wreck's physical deterioration. This monitoring would continue indefinitely, a commitment spanning generations of researchers. Some scientists argued for more active intervention. Proposals included deploying containment structures around the wreck, injecting sealant materials into the reactor compartment, or developing specialized robots capable of more extensive remediation at extreme depths. Each proposal faced the same obstacles: enormous cost, uncertain effectiveness, and risk of causing more harm during operations than the wreck was causing through passive leakage. The consensus remained that K-278 posed no significant threat under current conditions, and that monitoring provided sufficient protection against changing circumstances. The submarine would gradually deteriorate over centuries, becoming part of the seafloor geology. The radioactive materials would decay, their danger diminishing with each passing year. The Komsomolets disaster left technological and institutional legacies that shaped submarine development for decades. Russian submarine design incorporated lessons learned from the accident. Subsequent classes featured improved fire suppression systems, better protection for critical airlines, and enhanced crew escape systems. The Project 945 Sierra-class submarines, also built with titanium hulls, received particular attention after K-278's loss. Safety reviews identified and corrected similar vulnerabilities. Internationally, K-278 contributed to evolving discussions about military nuclear waste in the ocean. The submarine joined a list of nuclear vessels lost at sea: USS Thresher, USS Scorpion, and several other Soviet boats. Each wreck presented similar monitoring challenges and raised similar questions about long-term environmental impact. The International Atomic Energy Agency developed frameworks for assessing and monitoring such sites, drawing heavily on Norwegian experience with K-278. The accident also influenced thinking about submarine crew sizes. While automation offered operational advantages, the K-278 experience demonstrated that adequate manning for emergency response remained essential. Modern submarine designs balance automated systems with sufficient crew size to handle casualties. The Russian Navy's subsequent submarine classes returned to larger crew complements despite advances in automation technology. For Cold War historians, K-278 represented a particular type of technological tragedy. The submarine embodied Soviet strengths, advanced metallurgy, willingness to accept risk in pursuit of capability, and focus on performance over comfort. It also embodied Soviet weaknesses: inadequate safety culture, poor quality control in critical systems, and insufficient emphasis on survivability. The accident occurred during the final years of the Soviet Union, as the economic pressures that would lead to collapse were mounting. Some analysts have suggested that budget constraints may have affected K-278's maintenance and crew training. The human dimension of the disaster remained present in Russian culture. The 42 dead included young sailors on their first deployment and experienced officers with decades of service. Their loss resonated particularly deeply because most died after successfully abandoning the submarine, deaths that faster rescue could have prevented. The Komsomolets Memorial Society's continued work kept the accident in public memory, ensuring that lessons were not forgotten as the Cold War receded into history. Educational institutions used the K-278 case in training programs. Naval academies studied the accident's technical aspects, fire dynamics in confined spaces, high-pressure system failures, and emergency response procedures. Environmental science programs examined the wreck site as a long-term case study in radioactive contamination and ocean dilution. The accident provided data on human factors, decision-making under extreme stress, crew coordination during emergencies, and organizational failures in rescue response. The site itself became a kind of monument. While no physical marker exists at 1,080 meters depth, the wreck's location appears on nautical charts. Fishing vessels avoid the immediate area. Research expeditions treat the site with appropriate solemnity, conscious that 42 men died there and that their submarine remains a tomb. In subsequent years, additional revelations emerged about the accident's context. Declassified documents revealed that K-278's 1989 patrol had operational objectives beyond crew training. The submarine was testing its ability to operate in Norwegian Sea waters, where NATO maintained extensive acoustic surveillance networks. Soviet naval strategy in this period emphasized deploying submarines that could evade detection and threaten NATO shipping lanes in the event of conflict. K-278's depth capability was central to this strategy. The submarine could dive below the effective range of most NATO anti-submarine warfare systems. Its titanium hull enabled sustained operations at depths where conventional submarines could not venture. But this capability came at a cost. The specialized construction, limited crew size, and novel systems made K-278 more vulnerable to casualties than more conservative designs. The timing of the accident, in the final years before Soviet collapse, meant that some institutional knowledge was lost. Engineers and operators who understood K-278 systems were scattered as the USSR fragmented. The Rubin Design Bureau continued operating in post-Soviet Russia, but under difficult economic conditions. Comprehensive documentation existed, but the practical expertise of working with titanium-hulled submarines gradually dispersed. Russia's submarine fleet contracted dramatically in the 1990s. Many boats were decommissioned and laid up awaiting scrapping. Nuclear fuel was removed from reactors, but the submarines themselves often sat in crowded shipyards for years. This created environmental concerns across the Russian Arctic. The K-159, a November-class submarine, sank while being towed to a scrapping facility in 2003, creating another radioactive wreck in the Barents Sea at much shallower depth than K-278, potentially a more serious contamination risk. Norwegian authorities noted that K-278, despite its tragedy and ongoing leakage, represented a relatively well-documented and monitored case. Other Soviet submarine wrecks remained largely unstudied. Dumping sites where the Soviet Navy had disposed of radioactive waste, including entire reactor compartments, posed unknown risks. K-278's lesson was that international monitoring provided essential oversight, but this required cooperation from Russia, which was not always forthcoming. The submarine's legacy influenced naval procurement debates. Advocates for advanced, high-capability submarines pointed to K-278's achievements: the depth record, the titanium technology, the proof that extreme performance was achievable. Critics pointed to the catastrophic loss and ongoing environmental contamination as evidence that aggressive design approaches carried unacceptable risks. Both perspectives held validity, reflecting broader tensions in military technology development between performance and reliability. For the Norwegian Sea region, K-278 became part of the environmental baseline. Scientific surveys now routinely note the wreck's location and measure background radiation levels. Fisheries management incorporates awareness of the contamination source, though no restrictions on fishing have proven necessary. The ocean had absorbed the accident, distributing its effects across volumes of water so vast that human activities could continue essentially unchanged. Today, more than 3 decades after K-278 Komsomolets slipped beneath the Norwegian Sea, the submarine rests in cold darkness at 1,080 meters. The titanium hull, though damaged by fire and corroded by decades of seawater exposure, retains its basic integrity. The reactor compartment continues its slow leak of cesium-137 through the ventilation pipe. Ocean currents carry the radioactive isotopes into the vast water column, where dilution renders them undetectable within meters of the source. Norwegian research vessels still make periodic expeditions to the site. The monitoring program has become routine, part of Norway's broader environmental surveillance of Arctic waters. Each expedition collects water samples, documents the wreck's physical condition, and adds to the decades-long dataset tracking the submarine's deterioration. The data show consistency, gradual corrosion, intermittent leakage, rapid dilution, and no measurable impact on commercial fisheries or human health. The Russian Navy maintains its annual commemoration on April 7th. Ceremonies at naval bases remember not only Komsomolets' crew, but all submariners lost in the service of their country. In Zapadnaya Litsa, where K-278 departed on its final patrol, veterans and family members gather at a memorial bearing the names of the 42 dead. The submarine's history has been incorporated into Russian naval tradition, a reminder of sacrifice, technological ambition, and the sea's unforgiving nature. The wreck site itself remains undisturbed except for scientific sampling. No salvage operations have been attempted. The cost and risk remain prohibitive, and the environmental argument for leaving the submarine in place has grown stronger as years pass. The radioactive materials decay naturally. The ocean provides containment. Attempting to raise the wreck would concentrate the environmental risk at shallower depths and potentially release contamination during the lifting operation. K-278's story has become a case study in how nuclear submarines age in deep ocean environments. The 3 decades of monitoring provide data that inform assessments of other submarine wrecks worldwide. The Norwegian-Russian cooperation in monitoring, despite political tensions over other issues, demonstrates that environmental concerns can transcend geopolitical disputes. The sustained commitment to oversight shows that responsible nations can manage the legacy of Cold War nuclear programs. For the families of those lost, the submarine remains a tomb. The bodies of Captain Vaneen and most of his crew were never recovered. They rest with their vessel, entombed in titanium, and surrounded by the reactor they operated and the weapons they carried. The ocean above them teems with life. Commercial fishing continues. Research vessels pass overhead. The Norwegian Sea cycles through seasons unchanged by the wreck below. In time, centuries from now, even the titanium hull will fail completely. The structure will collapse, covering the reactor and torpedoes with sediment. The radioactive materials, decayed to insignificance, will become part of the geological record. The story will persist longer than the physical evidence, carried forward by those who remember not only the technological achievement K-278 represented, but also the price paid when ambition exceeded the margins of safety.